Good afternoon, everyone. It's my great pleasure to be here today, sharing with you our recent information on short and long-term performance of hollow core columns. I'm glad to be part of this session to memorize our friend and Asad Smaili. I have been with Asad on the ACI committee 441 for a few years, and he really contributed much to this committee and was very dedicated, very friendly. I joined after the committee while he was member before me, and he helped me to go through the different tasks and so on. So I really appreciate the help that he gave me and the friendship that he offered when we first met during the committee meeting. So I really missed him so much when I attend now the ACI. So going back to our effort at Missouri University of Science and Technology to develop bridge columns. So let me start with a quick introduction here about earthquake design, bridge columns for earthquakes, for earthquake loads. So if you have an axial load here applied to a columns and then you apply a lateral force, you typically would start with some tensile cracks followed by some concrete bulging and spalling, followed by some bar rupture, and creating, and bar buckling and compression, creating what we call the plastic hinge. And I typically think of a plastic hinge as this is a sandbox. Whenever you have your kids have too much energy, you give them the sandbox to dissipate the energy. And this is what the plastic hinge is. It's the sandbox where the earthquake can dissipate the input energy, without collapse of the structure. So keep that in mind. We try to avoid, we try to minimize damage in the plastic hinge zone, and also to work with ABC, which is accelerated bridge construction here in Missouri. So the way that we vision this is by developing new structure systems and also using advanced material. So let's start with the first system over here. Is the hollow core columns that consists of an outer FRP tube and inner steel pipe that was filled in between with concrete. So we have a concrete shell between the two pipes. If you think about a typical bridge column that has a diameter of 5 to 6 feet, the concrete shell would be only 4 to 5 inches. So a very thin concrete shell between the two pipes. This is just a demonstration. So this is not the right scale. It's just the demonstration of the cross section, how it looks like. So given the fact that you're going to remove a significant portion of the concrete from the core of the columns, you can cut the concrete use by up to 75%. The system is very lightweight. This is my former PhD student carrying the kind of a half a scale pipe that is, so this is like a 2 feet diameter glass fiber pipe. So it's a very lightweight. It also, when I said, ABC or accelerating bridge construction, the fact that we don't have any formwork, because the two pipe can be used as a stay-in-place formwork, which would accelerate the construction. Concrete cannot escape in anywhere because it's kind of confined from inside with the steel tube, from outside with the FRP tube. So literally, when we done testing, we get the concrete from from the column like in form of powder. So if you have a well designed tubes, concrete can really go far away. In terms of construction, we have two different options for the construction, either cast in place or precast. For precast, you will have, this is a shaded one here representing the concrete shell. So you will have the FRP and concrete shell, kind of shorter a little bit than the steel pipe. So the steel pipe would be provided, with some an extra length over there from, that will be used to to connect the column to the surrounding elements. So whether it's, for example, the footing or a girder. So the steel would be used to, the steel pipe would be used to transfer the moment between the different sections. So the other construction option is to use the cast in place. So this is, side by side for the precast. Sorry, for the cast in place, this is the cast in place. You will have the formwork and the steel for the footing, and then you have your steel pipe, and then fill between the two pipes with the concrete while pouring the or placing the concrete for the footing. In the cast in place, in the precast, you will have you place the footing, the concrete for your footing, and then you have a recess in the footing where you are going to place the column. And then you have the column coming, this is just a precast column, presenting a precast column. You have the column, this is the steel, for the joint. You insert the steel, you fill between, you see there is a gap here. I'm not sure if you see my mouse, but there is a gap between the steel pipe and the surrounding footing. So we fill this with high strength grout. And then we took this to the lab. This is our high bay lab at Missouri University of Science and Technology. Our colleagues here with the yellow hats, those are the engineers from Missouri Department of Transportation. Most of this work was sponsored by them. So this is testing the columns. So we applied the axial load using external post tension. This is applying the load back and forth. Of course, we accelerate. This was a static load, but we accelerated the video here. So we make the axial load. We mimic the lateral load by using back and forth loading. We inserted some videos inside the tubes so we can see what's going on. So this is a side of the steel pipe, and this is the bottom of the steel column. And as you will see here, this is just elastic buckling. So you see all this corrugation. This is the pipe, the steel pipe under compression. It's buckled, and now it would stretch back when it became under tension. And all those wires are just string gauges inside the steel pipe. Sorry. One of the crucial parts here for the design was to determine how much is the embedment length required for the steel pipe to provide a full mount capacity of the column. So that can be transferred for different elements. So we did some finite element work. We also come up with, an equation here, or we modified an equation from the literature, and we use a finite element, models to develop those modifications. So this is the equation here, and the red one is the best fit, and the blue one is the proposed equation or modified equation. So basically, this equation tells the engineer, if you have, what is the diameter of the steel pipe, the thickness of the steel pipe, the ultimate force on the steel pipe. So basically, the tensile force on the steel pipe, and then based on this, you can determine what is the required development length in terms of in inches. To investigate the required development length, we designed two columns. The first one had an embedment length smaller than what is required. And then we had another one with everything was the same except the embedment length. And you see here side by side, the one when we used a smaller embedment length, we get pull out failure and all the damage located at the footing. On the other one, you get a very minor hair cracks on the footing. Other than that, the column was able to develop full strength for moment capacity. So this was our way to check on the development equation that we developed. And if you look for the hysteretic loops here, so the moment versus lateral drift for this column over here, where we did not provide enough embedment length. So we were able to approach yielding. However, the column was not able to sustain too much deformations, and you see the benching over here due to sliding of the steel pipe from the column. Whenever we provided enough embedment length for exactly the same column, you see now the strength didn't really improve a lot. I saw a little bit improvement on the strength. However, mainly it is more energy dissipation and more displacement ductility occurred after that. When we worked with Missouri duty engineers, one of their concern is, well, the steel pipe is inside, and it's very hard to inspect the steel pipe. As you know, in the US, you need to inspect, roughly about every 2 years, you need to inspect your columns. So in order to give them kind of an idea what's going behind the fiber pipes and the concrete shell, we provided some sensors. I worked with my colleague here on the electrical engineering department. They developed a very unique sensors. So those sensors will be placed on the steel pipe, and then during the manufacturing process. So over here, those were placed on a column, cast-in-place column, and then once we have everything, they have their own like a special camera that can come and take pictures, and those pictures would penetrate through the fiber, the concrete, and then would let us know, what is the strain on the steel, and then you can use this for, documentation of the performance of the column during service life. Another concern for MoDOT was, it's, Saturday night, you have a drunk driver, or something similar, and then it hit the column. So we did we use LS Dyna to run finite element models for the columns, for the reference column, which is like a reinforced concrete column, and then for the new hollow core columns. So if you see over here, this is a damage to the trunk, and this is damage to the column to the right over there. The black lines representing the rebars and the hoop and all those, you see the damage. You see a lot of spalling for the concrete. So I'm just going to write again. So you see here the damage on the concrete, some over here. And based on this, actually, we propose a new equation for impact, vehicle impact loads on bridge columns for both for the solid sections, reinforced concrete sections, and also for hollow core sections. The new equation right now, the ASH2 is just use a constant value, 600 kips, load applied to the column. What we propose is based on the weight, the design weight of the truck, you can, as we give the engineers the freedom to design, to use an impact force based on the design speed and weight of the truck. Here is the impact on the hollow core columns. Because of the flexibility on the column, you see it's more like a total vibration on the column with really very limited local damage. And then, part of the issue over here is how this column is going to perform 20, 50 years down the road during service life. So we talked to Harry Potter here to use his crystal ball, magic ball here to try to see what will happen. And the way we did this is we placed those columns here, like a small scale of those columns. We subject them to a constant axial load, and we place them in environmental chamber. So this environmental chamber, and we have a ton of strain gauges, located on those tubes. So the columns inside the environmental chambers were subjected to 350 cycles of different environmental conditions. This include 50 cycles of different temperatures, moving from hot to cold and vice versa. We have another 3 times 50 cycles of different relative humidities, and so it's and also we have another 50 cycles of freeze and thaw. So typically we'll start with 50 cycles freeze and thaw. So if you see over here, this is the thaw and then freeze, 50 cycles like this, and then another 3 times 50 cycles of the temperature, and then 3 times 50 cycles with the relative humidity. So this was a very aggressive environmental conditions, and it was developed a while ago by Dr. Nani to summarize a severe weather here in the Midwest. And then once we subject the columns to the severe weather, we took those cylinders and we did two different types of testing. On one test, we did like, just, cyclic load on the cylinders to determine how the environmental conditions affected the not just the strength, but also the deformation capacity and the energy dissipation of the cylinders. And for those cylinders, we had two sets of cylinders. One of those where we used epoxy resin for the cylinders. So epoxy resin was quite expensive. So working with DOT engineers would like to look for a cheaper option. So we also did some cylinders with isopolyester resins, which is much cheaper than the epoxy. And then we also for other specimens, we get the concrete actually outside. We knock the concrete out, and then we cut the FRP in cylinder. So like rings over here, you see the ring, and we just did like a tensile test on the rings and the FRP rings. So this was some research on the columns. Working also with hollow core columns. Again, if you are familiar with seismic design for bridge columns, we have plastic hinges, and whenever this is, not like a very well designed plastic hinges, but just an extreme over here. So you see, like, you have those damage at the plastic hinge, and this is our success. However, if you look back, a few thousand years ago, we have those Greek columns that, were designed and constructed in high seismic zones, and they still intact. I think we should call this as the true success. And the magic here for those columns is they were constructed using segmental construction. So for segmental construction, when we started this project, we looked at segmental construction. We found it's very popular in the East Coast on the United States. However, we missed a very important thing. In the United States, we still use like a rebar. So once we have the segments, we have the rebar going through the segments, and we try to mimic reinforced concrete. So we end up very much with reinforced concrete columns. However, if you look for the Greek columns, this is my own picture. I took, I visited some of those locations in Greek and get those pictures. So if you look here for the columns, we don't have any continuity, like in form of reinforcement between the different segments. It's just, segments placed on top of each other. So during an earthquake, those segments will drop on top of each other, dissipating the input seismic energy. So, we have, like, if you think about like a bridge column, we take this bridge column to the left there, and we use like 1/5 scale. So this column here consists of like 4 different segments, and each segment consists of like, the hollow core section. So outside is glass fiber tube, the shell of concrete, and then the inner steel pipe. So, and then we have also unbonded post tension that going through the full column over there. So those are unbonded, from the section itself. And then the mass on the top of the column representing the inertia mass of the bridge deck. This is the shaking table, and this is like a relatively small shake table. This is why we need to have like a quarter scale of the columns. And you see here the tons of instrumentation that you did for the columns, and we subject those columns to near fault ground motions. So those are very aggressive ground motions. So here is the, this is a reinforced concrete column just at failure. So this is a conventional, well-designed reinforced concrete failure column with 1.2% vertical reinforcement and with a spiral reinforcement. So you see here, you have, nothing really surprise over here. You see a lot of tensile cracks. And then at the bottom, we have a very nice plastic hinge with rebar buckling and spalling of concrete. And then with the, this is a segmental column, was able to go 50% higher earthquake ground motion with no whatsoever damage, to the extent that we're not able to distinguish the tested columns from the untested columns whenever we have those on the lab. So we need actually to mark the tested column so we know, okay, this was tested, on the shaking table. Working also along the line with hollow core columns, This work has been done with, in collaboration with Professor Kawashima from Tokyo Institute of Technology. The testing has been done in Tokyo Tech. So I was a visiting scholar at that time, visiting professor at that time, and then we discussed this idea of four columns, that's segmental. He liked that, so we did this test. So on those tests over here, the top of the columns would be a conventional reinforced concrete columns. However, the bottom of the columns would be, this is where you have your plastic hinge, would be hollow core segments, and the segments would be ultra high performance concrete. So instead of the confinement and using the different pipes, over here it is just a UHPC, a precast UHPC segment that's placed on top of each other. Each segment has a height of about 2 inches, and then you see the holes over there. This is to pass whatever mild steel if you would like to get external energy dissipator. And then we did a hybrid testing. So we subject the column to a bidirectional equivalent earthquake ground motion. And this is just a comparison. Well, the energy dissipation for this is a conventional reinforced concrete. This is a segmental one. And, of course, the reinforced concrete column dissipated much higher energy, but it comes at a price, which is damaging the column. The segmental one, much smaller energy dissipation for a given earthquake intensity, however, with no damage. To improve the situation, we added some external energy dissipators, and those energy dissipators dissipated, increase you can tailor them for your earthquake demand. So over here, you see you move from the green. It is the same thing as the red one, but we added energy dissipators. So those energy dissipators, you can just go ahead and replace them after an earthquake with no, difficulties to access your columns. Looking at the residual displacement, this is the reinforced concrete column after testing. It has a very severe, this is a plastic hinge with a very severe residual displacement. And as I mentioned over here, those are the segmental columns. You can see it's very straight with no residual displacement. Looking at this is the residual displacement. So here is the reinforced concrete. So you see, at the beginning, the rest are just different design of segmental construction. So at the beginning, you see there is no more, much difference. However, all of a sudden, the reinforced concrete columns start to accumulate residual displacement, and all of a sudden, you see a very very high accumulation of those displacement versus the other columns, the segmental ones. This is also another way to look at the damage. We looked at the fundamental periods of the different columns, which again is higher periods. That's mean you get more damage in your column. So reinforced concrete columns, you see the elongation and the period as we keep testing, versus the other columns very much a very a minimal increase on this in the fundamental periods. And then we did finite element models over here to determine, to further investigate the behavior of those segmental columns.
Mohamed, if you can conclude in the next
and then we developed a design procedure. And with this, I reached to the conclusions. So we developed, with the help of my research team, we developed different sort of full core columns that can outperform the performance of well-designed reinforced concrete columns. We still have, we also developed a simple procedure for, to design those columns. However, we still have some challenges with those columns, for example, with the connections. And this is I would like to thank my students, our sponsor here, Modots Engineers, again, my students and all my sponsors. Thank you so much for your time. Thank you.